Today's our last lesson of Chapter 4. Chapter 4 is just a nice little mini chapter here. It says Lesson 4.4, Statistical Studies. And so our goal is that we want to be able to tell the difference between a sample study, an observational study, and an experiment. All right, so different statistical studies. So sample study is what we've already been talking about. And so a sample study is where you are trying to estimate a parameter or a variable for a population. Just copy down the stuff that's in red. You don't need to copy the blue down. You should already have that in your previous notes. So you're trying to estimate a parameter or a variable for the population. The main methods that we've discussed are simple random sample, cluster random sample, and stratified random sample. Okay, so that's what we've already done in that's what we did yesterday in lesson 4.3. Observational study. And so an observational study is where you are trying to estimate how two parameters in a population move together. The main criteria for an observational study is that you are watching or observing the population by collecting data of something that has already happened. Okay? So with an observational study, you're just watching. You're not doing anything. You're not trying to change anybody's behavior or anything. You're just watching or taking note of what has already happened and how does that affect anything. Okay. Then we have experiments. That's our third type of study. In an experiment, some kind of a treatment, and we call it a treatment. That sounds like kind of like a medical term, but a treatment basically is anything that we try to do or any kind of method that we try to change a behavior. And so it says, in an experiment, a treatment is imposed on the subjects as part of the study. This allows the researcher to establish a cause and effect relationship. Okay? So that's what an experiment is for. We're trying to establish a cause and effect relationship. And so there's some terminology out there that we're going to watch a little video here. It's called causation and correlation. And a lot of times people mix them up when they hear those two as far as what do they mean. Okay, so we're going to watch this little video quick.
Talk about the main types of statistical studies. So you could have a sample study, and we've already talked about this in several videos, but we'll go over it again in this one. You can have an observational study. Observational study. Or you can have an experiment. Experiment. So let's go through each of these, and always pause this video and see if you can think about what these words likely mean, or you might already know. Well, sample study we have looked at. This is really where you're trying to estimate the value of a parameter for a population. So what's an example of that? So let's say we take the population of people in a city. And so that could be hundreds of thousands of people. And the parameter that you care about is how much time, on average, do they spend on a computer. So the parameter would be for the entire population. If it was possible, you would go talk to maybe there's 1 million people in the city, you would talk to all 1 million of those people and ask them how much time they spend on a computer, and you would get the average, and then that would be the parameter. So population parameter would be average time on a computer per day. Average daily time on a computer. Now you determine that it's impractical to go talk to everyone, so you're not going to be able to figure out the exact population parameter, average daily time on a computer. So instead you do a sample study. You randomly sample, and there's a lot of thought in thinking about whether your sample is truly random. So you randomly sample, and there's also different techniques of randomly sampling. So you randomly sample people from your population, and then you take the average daily time on a computer for your sample, and that is going to be an estimate for the population parameter. So that's your classic sample study. Now, in an observational study, you're not trying to estimate a parameter. You're trying to understand how two parameters in a population might move together or not. So let's say that you have a population now. So let's say let's say you have a population of, 1,000 people. 1,000 people. And you're curious about whether average daily time on a computer, how it relates to people's blood pressure. So average computer time, or actually let me write it this way. Instead of average computer time, it should just be computer time. Computer time versus blood pressure. Blood pressure. So what you do is you apply a survey to all 1,000 people and you ask them how much time you spent on a computer and what is your blood pressure. Or maybe you measure it in some way. And then you plot it all, you look at the data, and you see if those two variables move together. So what does that mean? Well, let me draw. So if this axis is, let's say this is computer time, and this axis is blood pressure. So let's say that there's one person who doesn't spend a lot of time on a computer and they have a relatively low blood pressure. There's another person who spends a lot of time, has high blood pressure. There could be someone who doesn't spend much time on a computer but has a reasonably high blood pressure. But you keep doing this and you get all these data points for those 1,000 people. And I'm not going to sit here and draw 1,000 points. But you see something like this. And so you see, hey, look, it looks like there's definitely some outliers, but it looks like these two variables move together. It looks like in general, the more computer time, the higher the blood pressure, or the higher the blood pressure, the more computer time. And so you can make a conclusion here about these two variables correlating, that they're positively correlated. There is a reasonable conclusion, if you did the study appropriately, would be that more computer time correlates with higher blood pressure, or that higher blood pressure correlates with more computer time. Now, when you do these observational studies, or when you interpret these observational studies, when you read about someone else's, it's very important not to say, oh, well, this shows me that computer time causes blood pressure, because this is not showing causality. And you also can't say, maybe you might say somehow blood pressure causes more people to spend time in front of a computer. That seems even a little bit silly here, but they're actually the same, because all you're saying is that there's a correlation. These two variables move together. You can't make a conclusion about causality, that computer time causes blood pressure, or that blood pressure causes high blood pressure causes more computer time. Why can't you make that? Well, there could be what's called a confounding variable, sometimes called a lurking variable, where let's say that, so this is computer time, and this is blood pressure. I'll just write like that. Blood, looks like building. So blood pressure. And it looks like these two things move together. We saw that right over here in our data. But there could be a root variable that drives both of these, a confounding variable. And that could just be the amount of physical activity someone has. So there could just be a lack of physical activity driving both. Lack of activity. People who are less active spend more time in front of a computer, and people who are less active have higher blood pressure. And if you were to control for this, if you were to take a bunch of people who had a similar lack of activity, or had a similar level of activity, you might see that computer time does not correlate with blood pressure. That these are just both driven by the same thing. And what you're really seeing here is like, okay, in people with a high lack of active, or who aren't active, well, it drives both of these variables. So once again, when you do this observational study, and if you do it well, you can draw correlations, and that might give you decent hypotheses for causality, but this does not show causality, because you could have these confounding variables.
So one thing that the author is talking about right now is this correlation versus causability, or causation. And so correlation is what he's showing us right now. Two things might go together, but that doesn't necessarily mean that one causes the other. And that's a big misconception on people, and a lot of studies out there, and a lot of different reactions out there about different things. An experiment, and he's going to talk about next, is where causation actually can be proven.
Now, experiments are the basis of the scientific method. Experiments are all about trying to establish causality. And so what you would do is, if you wanted to do an experiment, you would take, and you probably wouldn't be able to do it with 1,000 people. Experiments in some way are the hardest to do of all of these. Maybe you take 100 people. 100 people. And to avoid having this confounding variable introduce error into your experiment, you randomly assign these 100 people into 2 groups. So random assign. So random. It's very important that they're randomly assigned. And that's nice. You might not know all the confounding variables there, but it makes it likely that each group will have the same amount of people with lack of activity, or that the lack of activity or the activity levels on average in each of the groups, when they're randomly assigned, it gives you a better chance that one group doesn't have a significantly different activity level than the other. And then what you do is you have a control group and you have a treatment group. Once again, you've randomly assigned them. So control and then treatment. And what you might say is, okay, for some amount of time, all of you in the control group can only spend, max of 30 minutes in front of a computer. And or maybe if you really wanted to do it, you say you have to spend exactly 30 minutes on a computer, and that's maybe a little unrealistic. And then the treatment group, you have to say you have to spend exactly 2 hours in front of a computer. And I'm making up these numbers at random. And it would be nice to see, okay, what was everyone's blood pressure before the experiment? And you can say, okay, well, the averages are similar going into the experiment. And then you go some amount of time and you measure blood pressure. And if you see that, wow, this group definitely has a higher blood pressure, this group has a higher blood pressure. So the blood pressure is higher here. And once again, some of this might have just happened randomly. It might have been, the people you happen to put in there, et cetera, et cetera. But depending if this was a large enough experiment and you conducted it well, this says, hey, look, I'm feeling like there's a causality here. That by making these people spend more time in front of a computer, that actually raised their blood pressure. So once again, sample study, you're trying to estimate a population parameter. Observation study, you are seeing if there is a correlation between two things, and you have to be careful not to say, hey, one is causing the other, because you could have confounding variables. Experiment, you're trying to establish or show causality, and you do that by taking your group, randomly assigning to a control or treatment. That should evenly or hopefully evenly distribute, not always, there's some chance it doesn't, but distribute the confounding variables. And then you on each group, you change how much of one of these variables they get, and you see if it drives the other variable. So anyway, in the next few videos, we'll do some examples of identifying these types of sample studies and thinking about what we can conclude from them, or these types of statistical studies, and see what we can conclude from them.
All right, so hopefully this was kind of a good just explanation of the 3 things. This observational study with the little chart down here, later on this semester, hopefully if we don't run out of time, we'll go through and do something like that where we're going to compare 2 things and we're looking for this correlation and how strong is it, all of those kind of things. Okay? All right, so back to our notes. Let me kind of make the screen bigger here. And so let's go to the examples. And so today, some of the things from yesterday will still be here, but we've got a few others added in. So it says, practice identifying the differences like we did yesterday, but now with the 2 new ones in the mix. Label each as a simple random sample, a stratified random sample, a cluster random sample, a census, an observational study, or an experiment. All right, number 1, to gather information about the validity of a new standardized test for 10th grade students in a particular state, a random sample of 15 high schools was selected from the state. They collected data from every 10th grade student in the selected high schools. All right, so we're grabbing 15 of them. So this would be a cluster random sample, and the reason why is because we're grabbing these 15 high schools and they should be representative of the whole state. So those are like the clusters. And then the other kind of key thing is we're polling or surveying every kid that's in the 10th grade for those. So that's kind of a key piece with the cluster. We take a census of our cluster that we're going to survey. Number 2, a school wants to know where seniors would like to have prom this year. So during homeroom, they have teachers give a survey to every junior and senior. So is that a simple random sample, stratified, cluster, census, observational study, or experiment? All right, so key thing, every junior and senior. We're going to survey everybody that could possibly go to the prom. That's a census. Flip the page. In the above scenario, the school decides to randomly survey 100 of the upperclassmen. Well, now we're not doing everybody, so it's not a census anymore. We're going to just randomly pick 100 people. And so that's that simple random sample. That's the easiest method and most common method to do. Number 4, suppose that 35% of the registered voters are registered as Republican, 40% as Democrats, and 25% as independents. A newspaper wants to select a sample of 1,000 registered voters to predict the outcome of the next election. They randomly select 350 Republicans, which is 35% of the 1,000, 400 Democrats, which is 40% of the 1,000, and 250 independents, which is 25% of the 1,000 for their sample. Okay? So when I look at this one, we are putting them into homogeneous groups based on their political beliefs or political affiliation, however you want to phrase that. And so that should be stratified. We're putting them into that homogeneous group, and then we're randomly grabbing people out of that homogeneous group. 5, researchers suspected that aspirin would help reduce the risk of having a heart attack. 700 people aged 40 or older were willing to participate in a study. Half of these participants were randomly selected to take an aspirin each day. The remaining participants were given a pill that looked like aspirin but contained no actual medicine. All right, so the key thing on this one is not so much how they selected the people, but what they're doing with them. Half were given an aspirin, half were not. So in that video, they talked about giving a treatment and having the control group. The people that got a pill that looked like aspirin but didn't have any medicine, that's the control group. And so this is actually an experiment we're conducting to see if the medicine really works, or sometimes we have something called a placebo effect where we give people medicine or fake medicine and it works just because they think it's supposed to work. Number 6, researchers suspected that tanning beds cause skin cancer. Each time a person was diagnosed with skin cancer, they were asked a series of questions, not a series, a series of questions including whether or not they had used a tanning bed. If they had, further questions were asked regarding how often, what type, and at what age. All right, so we're going to survey people, ask them questions about whether Okay, so in this one, it's kind of like the experiment, except we're not trying to change anything. We're just asking them what they've already done. And so that's an example of an observational study. We're studying people, but it's too late basically to change. It's what did they do in the past? That's what an observational study does. Okay? All right, statistical studies, I can tell the difference between a sample study, an observational study, and experiment. So it says, what is the difference between an observational study and an experiment? So an observational study is we're just watching. An experiment is we're actually doing a treatment or we're trying to change some behavior in the person. Okay? All right, go ahead and do homework 4.4 today. Tomorrow, you need to be ready for a quiz. So you're going to have to kind of study up on your own, and then we might add some additional things throughout the week if we feel there needs to be something extra to kind of study for. So make sure you're checking in the folder if you've done this earlier, if you've gotten this lesson done early.